Welcome, everybody. It's my pleasure to introduce Yohai Reani, and he'll be telling us about persistent cycle registration and topological bootstrap.
Thank you, Henry, and thank you for the opportunity and the invitation to present my work in this seminar. This work is part of my master's degree, which I did under the supervision of Omer Bobrowski at the Technion. Now I'm doing my PhD at the Technion in this, again, topology, random topology. And I'm going to talk about persistent cycle registration and topological bootstrap. And first, I'll start with the general framework of cycle registration. I'll start with a short motivation, and then the general setting, and then I'll talk about how we implement this method in the case of random geometric complexes. And in the end, I'll show some applications and the simulation results. Okay, so the motivation for this work is homology inference. So this can briefly described as the following. Assume that we have some space, and then we assemble this space. And now we are left with a set of samples. And we would like to reconstruct the underlying homology of the space from this sample. Generally, the underlying space is unknown. So what we do, first we compute the topological signature of this sample by, let's say, computing its persistent homology. Okay, so we start by computing the persistence barcode of the space. And then from this barcode, we would like to, this barcode or the equivalent persistence diagram, we would like to identify the cycles that represent the underlying homology of the original space. So a common approach is to consider the long bars, to relate the long bars to the significant features of the underlying space. So in this case, we identify the red long bar and the blue long bar as the signature, the real features, the homological features of the underlying space. And now the question that arises is how we determine whether a bar is long enough to be considered as a signal. So there is a nice work of Fuzzy et al. That addresses this question. And what they do, they start with a random sample from a manifold. And their output is a confidence set for the persistent diagram of this original sample. They compute the persistent diagram, and then they compute a confidence set for this persistent diagram. And the way they do it, in order to do it, they need to have some, to know something about maybe the underlying distribution, or instead use some method of bootstrap, which they do here. So they take the original sample and they generate additional subsamples from this original sample by sampling with replacement. And then for each subsample, they compute a persistence diagram. And then they compute the original persistence diagram to each of the persistent diagrams of the subsamples using a stability theorem and the bottleneck distance. Okay, and from these computations, they are able to compute confidence set, which are represented by, on the left figure, by these the squares around the points in the diagram, which each square, what it says that, let's say in this square, there is a probability, let's say 95%, that there is a feature in the original sample that falls in this square in the diagram. Okay, so instead of looking on these squares, they can look on a band over the diagonal, where they consider all the points that fall inside this band. These points, in fact, have a square that intersects the diagonal, and hence they can be considered as just trivial cycles that dies the moment they are born. And all the cycles that are outside this band are considered signal. However, you should note that this method is in fact compute confidence sets for the whole persistent diagram. Okay, it considers all the features together, And in addition, it does not take into account the spatial informations, the information of the cycles, of the different cycles. Okay, it used the numerical values of the diagram in order to compute the significance effect. What it says that if a cycle is far enough from the diagonal, then it's considered as significant. However, we believe that this is not always the case, as we show in the following examples. So consider the, let's say, the left example where we have some points sampled from an annulus, but with additional 4 outliers, as you can see. So below you can see the persistence diagram of this sample. And what we can see is that the cycle that is generated by the outliers have a large persistence. And it can be mistakenly be considered a signal, while we can see that this is not the case. On the right, we can see a different example where the signal is camouflaged by noisy cycles. Here on the right, we have some clusters that are separated, and hence the cycle that is supported on these clusters have a large birth time, and hence the persistence, the total persistence is short, and then we cannot identify it in the persistence diagram below. It doesn't stands out, the cycle of that's supported on the clusters. So generally, persistence does not necessarily imply significance. So instead, what we suggest is a different approach that utilizes the spatial information encoded in the.
Yohai, can I interrupt you with a question from the chat?
Yeah.
This was a question asked on the prior slide, although maybe it's also relevant to this slide. It's a question, does this have any bearing on undersampling? This seems to be a method for filtering out oversampling. That's the question.
I'm not sure, and can you maybe repeat again with more, what do you mean by undersampling?
So maybe the person,
Yeah, I'll ask. I'm the culprit. This seems like a method, right? You have various points in your persistent diagram, and you're trying to decide how robust they are, etc. But of course, if you're trying to understand the features of the space, you might not even see the cycle that's there yet. This seems like a way of filtering out cycles, but it doesn't necessarily tell you. This is right. I mean, saying, "Oh, I'm confident that this point is there," but it doesn't tell you about the things that you haven't seen. That you were hoping to see. Right. I mean, or at least it's not obvious. I mean, so that's what I was asking, whether there's anything in this method that deals with the problem. Right. I mean, there's, in theory, there are sort of 2 ways that homology gets wrong. Right. You might not have enough, and you might have too much. And it just seems like this a way of dealing with the too much.
All right, just a second. Yeah. Okay.
Okay. But anyway, I don't mean to hijack because it's 2 slides ago and etc. So.
Yeah. This method, as I understand it, they just go over all the features. They compute if you have a feature that is not necessarily appears in a subsample, then you take a point on the diagonal and you match between it to a point in the diagonal. So maybe sensory mentions, or maybe I didn't understand. But generally, this work, what they suggest, that this is a method in order to determine when a bar is long enough in order to be considered significant. This is the idea behind this method. Maybe after we go offline, we can maybe explain the question again. Okay, so what we suggest is a different approach. Again, we have a sample X, and let's assume that during this process of persistent homology, we observed some cycle gamma. And now we define the following score, which we call cycle prevalence, which is just the probability that gamma will appear in a new sample. Assume that we can generate a new sample from the underlying distribution. And so we want to answer the question, what is the probability that gamma will appear in this new sample? Okay, so we have a new sample. You can see that we have a cycle similar to gamma in this new sample. And then the key challenge now, which leads us to the main contribution of this work, is how we determine that two cycles that are supported on different spaces or point clouds represent the same underlying feature, homological feature. Okay, so the main goal is to provide such framework that enables us to do matching between persistent cycles of two spaces. Okay, and the challenges are first the topological challenge. How do we determine whether two cycles match? And the second one is computational, how we implement this framework. Okay. So we start with the first topological challenge. How do we decide how to decide whether the two cycles match? So generally, we can describe this problem in the following way. We have two spaces in question X and Y, and we would like to compare their homologies by matching, by finding matching cycles that represent the same underlying phenomena. And there are several works that address this question, and one recent work is the work of Yoon, Grace, and Justy. Justy gave a talk in this seminar a few months ago. This work called Persistent Extensions and Analog Paths. And what they suggest, they start with 2 point clouds. They compute the Rips complexes, and then they compare these complexes via a witness complex. And they use the Docker theorem and other stuff and the other ideas they present. And they require to have cross dissimilarity measure between the vertices of the spaces in order to do this matching. In addition, they for each individual cycle, they found all the, let's say each individual cycle in X, they found all the possible matching in Y, and then they do some sort of optimization process in order to select the cycles that best represent the original cycle. However, what we are going to do is a bit different. First, we are going to, I'll show you the following, or maybe I'll just continue to what we do, and I'll describe the differences. So we start the similar way with these two spaces, X and Y, that we would like to compare their homologies, but we assume a different thing. We assume that we have some third space, Z, which we refer to as a frame of reference, such that X and Y are both mapped to this space Z. The maps that map these spaces to Z then induce maps in homology between the homology groups of X, Y, and Z. And now we define the matching condition in the following way. We say that a cycle in X matches a cycle in Y if both cycles are mapped to the same non-trivial cycle in Z. Okay, is it clear? Okay, so this description is for fixed spaces. And now we would like, the next step is to generalize this description to persistent cycles. However, this a bit more challenging, since in the case of persistent cycles, each persistent cycle has its own birth and death times. And we are looking for some point in the filtration where we have two persistent cycles that are mapped to the same persistent cycle in Z. So this becomes much more challenging. So formally, we have, instead of fixed spaces, we have filtrations. And let's say that at some point in time, we have these spaces. You can think about the filtration as the sub-level sets of the distance function from these spaces. Now, let's say that X is mapped to the top part of this ellipsoid Z, and Y is mapped to the bottom part. And as we can see, the red cycle in Z and the green cycle in Z both represent the same cycle in Z. they are two generators that represent the same topological feature. Hence, we would like to argue that gamma and delta, which are cycles in x and y, the corresponding cycles in x and y, are matching cycles. This is what we would like to have. Okay. So the question that arises is how we identify such cycles in Z that can be represented as from the perspective of X as a cycle in X, and from the perspective of Y as a cycle in Y, as we can see in the middle cycle here in Z. We look for this kind of cycles that serves as tunnels from the image of F to the image of G, in fact, and that don't have any hole in the middle. So the way we are going to do it is by using a notion called image homology, which was presented by Edelsbrunner and al. And this idea is a very simple idea. Assume that you have two spaces X and Z, and X is mapped to Z to F. The map F induces map between the homology groups of X and Z. And then we can define the image homology of F as just the image of F star. Okay, so for example, if we look on fixed homology, then assume that we have this cylindrical space Z, and X, let's say it's top cover, and the map F is just the inclusion map. Okay, so as we can see, in X we have two non-trivial one cycles, but only one of them is mapped to a non-trivial cycle in Z. The other one is mapped to some sort of cup. So we say that the first homology of the first image homology of F is just its dimension is just one, since it includes only one cycle. It contains only one cycle. Okay, this idea can be generalized to image persistent homology. So now we consider filtrations instead of fixed spaces. So Z is the filtration of the cylinders below, and on the top we have the filtration of the axis, which is the top covers of the cylinders below. And we see that at the second level of the filtration, there is a cycle that is born in X, and this cycle is mapped to a non-trivial cycle in Z. Hence, we say that an image cycle was born at time 2, okay, at level 2. This cycle, we continue the filtration. This cycle continue to persist in X, but in the third level of the filtration, this cycle is mapped to a trivial cycle in Z. Hence, we say that the image cycle that was born at level 2 died at level 3. And we can represent this the same way we represent persistent homology with a persistence barcode diagram. Yes.
And there's a question from Shmuel again. Shmuel, please feel free to interrupt if you like. But he asks, how does the map behave with respect to the filtrations? Does it commute?
The map of F, you mean? The map.
Yeah.
Yes, F. Are you assuming that F of X sub T is inside of Z sub T? Or
yeah. So if we restrict F to let's say F2 to F to X1, then we get F1. So
okay, I mean, right, but just so this wouldn't give a way of checking if I was looking at cycles from, say, two different if I was using sub-level sets of functions instead of samples, and I was taking two different functions on the same space. For example, right? I mean, this is really adapted to, two different samples that are around the same level of density.
Okay.
Right?
Yeah.
Okay. So I'm just trying to, look at some of the missing words. Okay, thanks.
You're welcome. Okay, so now we take this idea and we utilize it in order to identify matching cycles, and we do it in the following way. So again, we are getting back to previous example. We start by computing the persistence homologies of X and Y, the regular persistent homologies. Then we compute the image homology of F, the persistent image homology of F, and the persistent image homology of G. Okay, I put these diagrams aligned. They have the same scale. Okay, and now what we do, we look for cycles in Z that have yes, we look for image cycles that represent the same topological feature in Z, the same homology class in Z. And now we identify these classes. We identify them by the death time. Okay, since if you look on the middle, we have the red cycle and the green cycle, both represent the same cycle in Z. So once this cycle in Z dies, both image cycles die. And we represent this relation with this vertical yellow dashed arrow, okay, between the diagrams. Now we find we match each image cycle to its to the cycle that was mapped to it. Okay, so we take the red cycle, let's say, in Z, and we find the source of this cycle by just connecting the cycles with vertical lines in the diagram. And the reason this is true is because it derives from the definition of the image cycles, which says that an image cycle is born when a cycle, let's say in X, is born, and this cycle is mapped to a non-trivial cycle in Z. Hence, the image cycle and the cycle in X have the same birth time. This, like, okay, is it clear? So now what we have a path.
Yohai,
yeah.
Can I ask you a quick question? So from the image, it seems clear that F and G are inclusions. Is this?
So this is just for illustration purpose.
I see. So the inverse might not be unique. In other words, there might be different.
Yeah. So we do limit ourselves to unique. In the paper, we address this issue where you don't have uniqueness, and then maybe this framework won't give you the expected result. So we limit ourselves to maps that have a unique mapping. This is mostly the case in random samples.
Aha, thank you.
As I'll show next. So now we identify matching cycles by searching for a path that connects a cycle in X to a cycle in Y through these diagrams. And as we can see, we have a path that connects the red cycle and the green cycle, hence which are gamma and delta, in fact. Hence, we say that these cycles are matching cycles. So, so this was the general setting. Okay, in the case where we are talking about spaces, and now we want to talk about the implementation of this framework in the in geometric complexes. Questions?
David has a question in the chat. So what in general can the functions f and g be, and then what are you considering in this particular case of interest? So you're particularly interested here in inclusions of subsamples, but in general, could they be any maps between topological spaces, any continuous maps?
No. So they need to have. Let's see. I did it a long time before. There is some restrictions on these maps. Wait, did I just went to? I believe they're supposed to be one-to-one, but I'm not sure. I can check it later, and I can give you a more robust answer. Yeah, but I don't remember exactly now the exact properties.
No problem.
But there are restrictions. There are restrictions.
Okay.
If they are one-to-one, it's supposed to.
Then that's totally fine. Cool. Thanks. Yeah. Please go ahead.
Okay. So now we're going to talk about the implementation of this framework in the case of random geometric complexes. So briefly, let's go about the most commonly used ones. So given a set of points X, the check complex is defined as in the following way. In fact, as the nerve of this ball cover that we see on the right, which means that the simplex is in the complex if the intersection of the balls centered on its vertices is non-empty. Okay, so I believe everyone here are familiar with this complexes. The Vietoris-Rips complex is defined in a similar, in a different way. Simplex is in a complex if its pairwise vertices distances between its vertices is less than 2r, when r is the radius of the balls. Okay, as you can see in the illustration on the right. So now we go back to our cycle matching framework. So assume that we have 2 point clouds x and y, which we sample from the same distribution. And now we propose the following frame of reference, following a common space, by just taking Z to be the union of these point clouds. This is, we believe, the natural choice in this case. And now what we get is the following. Since X and Y are included in Z, we have the check complexes are also included in the check complex of Z. So this provides us with the required maps that we need in order to do our matching. In this case, the required maps are just inclusion maps. The same holds for Rips complex. And now we can get something like this. We have 2 check complexes X and Y. Both are mapped to the check complex built over their union. And now we can identify matching persistence cycles between this filtration using the method we presented before, image homology and all of this. The problem with this approach is that these complexes grow quite fast with the dimension. Instead, what we suggest, this is a different work, we suggest to use to replace the check complexes of of X and Y with alpha complexes, and the intermediate complex we replace with a new complex we call the coupled alpha complex. We have a paper that we available online that you can see. I won't talk about it more, but I'll just say it based on the alpha complex, and its computation is significantly less costly. So you can look it online. So now that we know how we're gonna do the matching in the geometrical complex space, we turn back to the problem that we started with. Yes.
And Yohai, could I ask a question?
Yeah.
There's a question in the chat on the relationship with zigzag persistence. Do you think of this as being related, or?
Yeah. So one of the papers that when we start working on this problem, we encountered the zigzag paper. We use a similar method. You take this series of inclusions, and then you have a series of inclusions that goes both directions, where you have a space and inclusion, another space and inclusion, and so on. There they also give a similar idea of computing the significance of cycles by just counting the persistence of the zigzag series.
Suppose this is a very short zigzag here.
So exactly. So this is a one-step zigzag, in fact, and we also discuss this in the paper. In the zigzag case, the problem is that.
Oh, Yohai, somehow you accidentally muted yourself.
Sorry.
There you go.
Yeah. So in the zigzag case, once you look at a certain cycle and you go through this zigzag series, then it can be that this cycle at some point dies and then born again at a later point, and it's and the problem is you can't relate between these two bars, and so yeah. So, but we have a short discussion on this in the paper. Okay, so let's continue. So we go back to the topological bootstrap problem that we started with, the homological inference. And first, before we proceed, we want to explain what is a statistical bootstrap. The concept of statistical bootstrap, which first was presented by Efron in 1979. And the idea is basically enables one to estimate the statistical properties of estimators when the underlying probability from which you draw the sample is unknown, or maybe even if it's known, computing the statistical properties is hard. Not practical. So instead, this is a computational method that enables you to study the properties of estimator based on some approximating distribution, which is based on the sample that you have. So, for example, if you take, let's say, a set of points that we sampled from some distribution on the real line, and we would like to estimate the mean. So we can compute the mean estimator, which is just the average of these points. And now we would like to have additional information, maybe the variance of this estimator, in this case, in order to say how confident we are that this value is, in fact, represent the real value, or how close it to the real value. So what we do, since we have only one sample, we generate additional samples by sampling with replacements. And for each such sample, we compute its own mean estimator. And now we can compute the mean of all these estimators, and we can plug it into the formula of the variance, empirical formula of the variance, in order to get estimate of the variance of this estimator. So the idea is using subsamples in order to assess the accuracy, let's say, of an estimator. So we would like to use this concept in some or similar concept in our cycle prevalence problem. So recall that we had a density and we had a sample and some observed cycle. So what we do, since computing the probability that gamma appears in a new sample is very hard, what we do instead, we just generate additional samples. And now we would like to use our cycle matching method in order to find matching cycles in these subsamples. And we, instead of, and we approximate this distribution, the cycle prevalence, is just by counting the times that each cycle appears in the subsamples. So we take the original sample, we compare it to each of the subsamples and check how many times each cycle appeared in these additional subsamples. Just compute this approximation. Yeah, there is a question? No, okay, continue. Okay, so this can be done also from the original distribution, okay? Since computing these probabilities, even if we know the underlying distribution is not clear exactly how to do it, it can be very complex. So instead we use some subsampling method in the following way. Generally, F is unknown. So we generate these subsamples. We from an approximate distribution, in our case, we use the kernel distribution estimator, which is just a sum of Gaussians centered at the points of the original sample X, where H controls the variance. This is equivalent for sampling with replacement, but with an added small perturbation. And the reason that we add a small perturbation is to avoid degeneracies that are related to the construction of the geometric complexes. We don't want to have two vertices at the same point in space. Okay, so now it seems like we're done, and we can continue and show our framework excel on different experiments. But when we started experimenting, we found that we had the following problem. We saw that as sample size grows, the noisy cycles in our sample tend to be prevalent, meaning that their score is high. So let's say we take, so what we did, we just took 1,000 points in the unit square. And as we know, the unit square is contractible, hence it doesn't have any, its homology is trivial. It doesn't have any cycles from a dimension that is larger than 0. However, when we computed the cycle prevalence, which is in fact the frequency, what we saw that there are cycles, as you can see here, that tend to be prevalent. Here we see the first 20 most prevalent cycles. So this is a big problem for us, since our first intention was to come with some score that will enable us to distinguish between signal and noise. And this clearly doesn't let us do it. And when we looked inside these cycles, on the right, you can see, on the top right, you can see the most frequent noisy cycle, the original sample. And when we look into the subsamples and we looked on its matching cycles, we saw their structure varies very much between different subsamples. And we then realized that maybe we can utilize the information on these persistent cycles, meaning the length of the intervals, in order to get maybe define a more qualitative cycle matching. And what we did, we defined the overlap coefficients. So let's assume we have two cycles that match, gamma and delta, and these are their intervals. So what we do, we just take their union and their intersection, and we compute the ratio between them. And this is, and with this we define as the overlap coefficient. And now back to our cycle prevalence problem. For each gamma in X, instead of computing the number of times it appeared in subsamples, we compute a more finer measure, which takes into account the quality of matching between gamma and delta I, and gamma to its image cycles and delta I to its image cycles. Okay, this is the heuristic that we chose. And if we go back to the example of noise, what we see that while the cycle frequency is very high, using this finer cycle prevalence gives us much better results as we expect. We get low scores as we expect for noise. Yes, is there any question? Continue? Okay, I'll continue. Okay, so now for some simulations. So we started with a simple simulation on the torus. So we sampled 1,000 points uniformly for a torus, from a torus. And then these are the properties of the torus. Our center is the radius from the center of the torus to the center of the tube. And R tube is just the radius of the tube. And H is the parameter of the kernel density estimator, its variance. So what we got is the following. So on the top left, we can see the data, the sample data. And on the top and the bottom left, we can see the persistence diagram. As we can see, we have two cycles that stands out far from the diagonal. And in fact, these cycles are the cycles, the one-dimensional cycles of the torus. We are looking only on the one-dimensional homology. On the top right, what we can see is that our method agrees in this case with what we expect. What we can see is the first 10 cycles that are most prevalent. And we have two columns that stands out, two prominent columns that in fact relate to the cycles of the underlying torus, as we can see on the bottom right. Okay, the red cycle is the one encircling the center of the torus, and the blue one is encircling the tube. And the columns that we see, so the blue ones are for samples that are generated from the underlying distribution. We assume in the blue ones that we know the underlying distribution. And in the red one, we use the kernel density estimator with the parameter h. As we can see from samples drawn from the original distribution gives better results, but still we can identify the right cycle. The second example is the same as the first examples, but now we took the first example to the limit and we sampled only 100 points. So the sample is much less dense. The parameters of the torus are the same, and what we get is the following. So as you can see on the bottom left, now in the persist diagram, there is only one cycle that is clearly stands out, and the second one is it's more hard to identify. And on the right, you can see our cycle prevalence. Again, the blue one is the new samples generated from the original distribution. As you can see, we have two cycles that stands out, and when we draw them, we indeed get the right cycles that we expect. For the resamples, the results are less good. We believe that maybe we can make these results better if we maybe tweak a bit the parameters of the kernel density estimator, or maybe use different ways of estimating the underlying distribution. Another nice example is the examples of clusters and noise, as we saw in the beginning. Here we took 5 clusters and we played with the ratio between the number of points in the clusters and the number of points on the background. So what we do here, we sample 500 points, and each point we sample with probability p to be on the clusters or to be in the unit square, or 1 minus p to be in the unit square. So the top example is when we take p to be 0.3, meaning there are much more points in the 30% of the points are noise, 70% approximately are clusters. And what we can see on the diagram on the right, that it's hard to identify the cycle that is supported on these clusters. The blue point is the cycle supported on these clusters, and it's hard to distinguish between the cycle and the noisy cycles, since in fact we put some bound on the birth time, lower bound on the birth time. And on the bottom, again, it's hard to identify this cycle. But on the right, as we can see in the first case, in the blue, for P, for a low amount of noise, we clearly can see a signal in this sample. And for if we take P to be larger, then the signal diminishes, but still maybe it can say that there is something in this sample that is worth looking, worth checking, that maybe there is some signal that is hiding there. Okay, so the next application that I would like to briefly discuss is similarity measure that we suggest that is based on our cycle registration framework. And the idea is the following. So we call that the Wasserstein distance is a measure of distance between persistent diagrams. And generally what it does, assume that you have two diagrams, the blue points and the red points. First, we would like to give some measure of distance to these diagrams. So what we do, we find the best matching between these diagrams. And then we compute the pairwise distances of these pairs. And this gives us a measure of distance between these diagrams. This distance is widely used. However, there are some cases that maybe using this distance is maybe will give us results that are maybe not agrees with our intuition. So let's, for example, consider the following for example. So here we have three spaces x, y, and z, and the black point in the middle of the spaces represent the origin. Okay. So now assume that the filtration we are looking at is the sublevel sets for the distance functions from these initial spaces. Okay. We compute. Okay, so first we notice that x and y are very similar. Yeah, y is a thick version of x. However, z and y does not seem to be a similar spaces. So we start by computing their persistence barcodes. And we made this example in a way such that the Wasserstein distance between x and y is 2. However, if we consider the Wasserstein distance between z and y, we get 0 in this case, since the bars are very similar. In fact, their cycles have the same persistence, though they have a different structure. So what we suggest instead, we suggest to use a similarity measure we call the guided Wasserstein distance, which replaces this optimization, the best matching in the Wasserstein distance with just our cycle registration framework. So what it means that we identify matching points between the diagrams if they are matching points according to our cycle registration framework. And now what we get is a distance that is larger than the left distance, since it's the best matching on the left. And as we can see in this example, when we use our framework and we map this, we use the inclusion maps and we map x and y to their inclusion, their union, we get that the top cycles, the outer cycles are mapped to the same cycle and the inner cycles mapped to the same cycles. Hence, the distance is computed between these pairs. And again, we get the same distance as we computed before. However, now only the inner cycle of y is mapped to the left cycle of z, while the right cycle of z is mapped to a different place in space. Hence, there is no matching between the bottom barcodes. Though these barcodes are associated with points on the diagonal, which results in a much larger distance, which now does agree with our intuition, with our first intuition that x and y have the same structure, similar structure. So to conclude, so what we saw, first we started with the cycle registration framework. And basically what we do, we match between cycles of two spaces based on the common space, which we refer to as a frame of reference. So we require a frame of reference. We use the notion of image persistent homology together with birth-death times, which enables us to do the matching over the diagrams, as we saw in the example, rather than do something in the space itself. So it's enough to use the diagrams in order to do the matching, under mild assumptions that the birth and death times are unique, which in the random case is the case. And this cycle registration can be used in any setting where a frame of reference is available. Let's say you have two sensors that measure the same scene, and you know how to align this sensor, then you can use this frame of reference. Or let's say in a medical imaging cases, where you have slices and some 3D risk construction. In homological bootstrap, what we saw, so the general process is first we start by generating subsamples from the original sample. Then we find, using our cycle registration method, matching cycles in subsamples, and then we compute the cycle prevalence, which which gives us the significant, it tells us which cycles are significant. For future works, what we like to do is to develop this method more. For the homological inference, we believe that with some parameter tuning or the cycle prevalence that we suggested, this final cycle prevalence is just a heuristic. We can maybe find a better cycle prevalence score that better represent the significance. For the guided Wasserstein distance, we would like to develop it and to maybe things regarding to stability and study its product properties and hopefully find more applications that we can use cycle registration, and the cycle registration can maybe help to give good results. So you can find this work online, and this is the first paper. There is another paper, a coupled alpha complex, which I discussed briefly, which also you can find online, which is a structure that we use in our cycle registration, and all the code for these papers, you can locate it in GitHub under this address. Yeah, you can try it yourself to play with it, with the simulation that you saw, and maybe use your own data. And thank you very much again.
Thank you very much. So before we get to questions, let's applaud for the speaker. All right, further questions for Yohai?
I actually have two questions, if that's okay.
Yeah.
One of them is a stupid question, but for the sake of fairness, I won't say which is which. So the first question is, so from a computational perspective, I'm wondering, suppose you had the following idea, which is that you bootstrapped, and you restricted the number of points that you were allowed to sample. So you started with 1,000 points, but maybe you only allowed yourself to subsample 100 points, maybe with or without replacement. Computationally, it would be simpler, and also maybe you would, you maybe get a sense of which topological features are present if you limit, the number of points, which could somehow filter out some kind of noise. Do you think that's a reasonable idea?
So this method enables you to use you can subsample use smaller samples. But again, maybe you can miss some cycles that once you take smaller, maybe your second space won't be dense enough, second point cloud, to capture or to find matchings to the original cycles. So,
I see.
But in terms of computational computation, maybe good practice. Sample is very large.
And the second question is, so first of all, thanks for the answer there. The second question is, if I understand correctly, this method is based on registration between two pairs of between sort of a pair of point clouds, pair of spaces. So putting aside computational ability, do you think this idea could be generalized to, I give you n point clouds and you want to find something which, maybe it's horrible to compute, but something, at least the math would work out, that somehow a common registration of, say, 5 different point clouds is different than 5 separate pairwise registrations that you all somehow register at the same time. I'm not sure what that looks like, but you think that's a coherent idea? Maybe this is the stupid question. A coherent idea, or is this completely bananas?
So it's an interesting question first, not a stupid one. Makes me think. So when we worked on the coupled alpha complex, so the idea there is we embed point clouds in a larger dimension in order to get a simple complex that include both alpha complexes. And there, what we noticed that maybe you can do it for not only for pairs, you can do it for maybe more than pairs. In terms of homology, I'm not sure what to imagine exactly, but let's say we have a cycle that goes from X to Y and from Y to third space W. So is it possible that we have like triple match in this scenario, or in this case, it just says that the cycle that goes, the tunnel that goes from X to Y has another opening that goes to a different space, which not enables us maybe to match these two cycles in X and Y. I'm not sure, but it's interesting, but maybe I believe this is what you mean, right? So like a cycle that is like to do everything in one time, maybe take all this some symmetric matching.
Maybe, well, I'll let you move to other people's questions, but that's an interesting, development of what I was asking. Thank you.
Thank you.
David, please go ahead.
Okay, thank you, Harry. Yohai,
Yes.
my question is still on the mathematical concepts of your mapping. I don't know if you can go to that slide.
Again?
The mapping between X, Y, and Z.
Yeah, so I believe what we required is just that this map will be, let's say.
No, the first mapping.
In
the one
matching,
you look at the cycles.
You mean this F and G?
Yeah, this map. Yeah.
Yeah. Okay. So if we require this map to be, I think one to one, then we can this matching thing works. If it's not one to one, then you can get weird things. Like let's say two vertices. I think I have an example for this on the paper. I have an example for this. Two vertices that goes to the same vertex, and thus you can have a cycle that is mapped to maybe a trivial cycle. While
I think since I'm coming from the pure aspect, from the pure mathematics aspect, I would like to know the mapping that you between X and Y, and that is from X to Z and Y to Z, and you had two functions, the F and G. I don't know if F and G are homologous, like the two functions are similar, or there are no similarity between F and G.
F and G does not have to be similar. It can be different, let's say recording of different sensors, and the maps can be different. You can have different properties, but
Did you sort of trying to measure how similar or different they are?
So F and G are not similar from the work. They are not similar.
They're not have to be similar.
Similar, okay. And also because you
Just to
had two
exist.
spaces, X, Y, and you have Z to be your third space. And you have a cycle in X, and you have a cycle in Y, and you have another cycle in Z, if I'm getting what you explained. So you have these two cycles in Z, then you map a cycle from X to Z, and another cycle, the cycle in Y to Z. And you have a function F and G. But I think your space Z, you chose a space Z. That is from the work, you chose the space Z. Was the space Z chosen, or they have an underlying property between X, Y, and Z? Did they have any property that you are mapping the cycles to? Because it seems like you map it exactly from one cycle to the other. That's why I don't know. So your F is supposed to be a continuous map, and Z is also going to be a continuous map from your work. That's what I'm getting.
Yeah. So in fact, the maps are maps between the homology classes, and these cycles that I draw are illustrations. So in fact, the shape of the cycle is not necessarily the same. The red cycle in X is not necessarily looks the same when you look at it in Z, but it has the properties that it's more an interval matching rather than a cycle matching. If we want to talk about generators, specific generators, then we have some weird things that we also discuss in the paper. And it makes the problem much more complex. I believe that in the work of Justy, what they do, they look on a basis, on a specific basis, and they choose basis, and for each basis element, they found all the homological cycles. So here what we do is just is a map between the barcodes more than a map between geometrical generators.
Okay, if there is a map between barcodes, I think the computational will be okay. If I understand your point of reference, that you're mapping the barcodes, not the geometric notation of it, like the geometric features of the two maps, but rather the barcodes that they represent. I think that
it would happen. Yeah, it would happen that you have similar generators. Yeah, like in the torus case, when you look on the real signal, then you get the same. The generators have the same structure since they are at the end they are circling the center. Yeah, but the noisy cycle, let's say, have different characteristics. So,
okay, I think I get it. I thank you so much. That's a nice presentation.
So maybe we have time for one more question on the recorded portion. Any final questions? I'll ask a question, Yohai. So at one point you mentioned how you perturb the points so that you don't have overlap. What's the problem with overlap in this setup?
So basically, when you compute these complexes, then you want to have you want to get simplexes again. Yeah, you don't want to have some degeneracies. Yeah, like a simplex that is supported on 2 points that are the same point and stuff like this, which can later maybe interfere with your computation of the persistent homology. It's more maybe when we compute this stuff, we use the alpha complex, and the alpha complex. One of the steps is compute the Delanoid triangulations, and once you have degeneracies, this computations doesn't give you unique complex, which interfere with this matching.
Gotcha. Well, great. Thank you so much for the fantastic presentation, and thanks everybody for the questions today. So let me at least end the recorded portion here.
Okay.